We're going to consider moments and centers of mass now, and for this we're going to look at the idea of masses located at given points. M1 is 5 and it's at a location -4, 2. This is on the xy plane. M2 is 4, located at 0, 5. M3 is 3, located at 3, 2. And M4 is 6, whatever the units are, located at 1, -2. Let's plot these. We now have these masses plotted on the xy plane. And what we're ultimately after is if we had a situation where we had a thin plate, let's say, and masses were situated at these positions on the plate, then where would the balancing point be? Probably somewhere interior to all of the, certainly somewhere interior to all the points, probably somewhere around 0, 2 or something. But in order to come up with that idea of the center of mass, we're first going to consider something called moments. Don't ask me why they're called moments. Now, a moment is a tendency to rotate. And when we talk about the moment about the y-axis, it's the tendency of this system here to want to flip either to the left or to the right. So we have this single mass over here in the second quadrant. It's a mass of 5, and it's at -4, 2. And its location is 4 units away from the y-axis. And then we've got this other mass over here, a mass of 3 at the point 3, 2, and it's 3 units away from the y-axis. If those were the only two that we had, then they would be fighting each other, and this system would want to flip either towards the second quadrant or towards the first quadrant. Incorporating now that we have a mass of 6 at 1, -2, we're now 1 unit to the right of the y-axis, and so it seems like maybe this 3 and the 6 are going to add together and want to flip the system over toward the right side, like toward the positive x-axis. But we're not sure that that's actually the case. But the idea here behind a moment is we're going to take the mass, one of the masses that we're given, and multiply that by the distance from the axis that we're talking about. And so that's one computation that we're going to make here. But then we're going to add together all of those moments for all of the masses. So the moment about the y-axis, m sub y, is equal to the sum as I goes from 1 to n of mi yi, nope, that's mi xi, the mass times the distance from the y-axis, and x is defined to be that distance. So in our case, that looks like 5 times -4 for the first mass, 4 times 0 for the second mass, which is on the y-axis, so the distance is 0, 3 times 3 for the third mass, and then 6 times 1 for the fourth mass. Adding those together gives us m sub y is equal to -5. That the moment about the y-axis is negative means it wants to flip to the left. And even though we have this the mass of 3 and the mass of 6, and those, well, they add up to 9, the mass of 5 is farther away from the y-axis, and so it contributes more to the tendency to want to rotate. Now we can consider the moment about the x-axis. And I actually want you to pause the video, see if you can write down a sigma notation that will tell what m sub x is, and then see if you can do the computation. Go ahead and pause now. And what we should have written down is that m sub x is equal to the sum as I goes from 1 to n of m sub I, y sub I, y again being the distance from the x-axis. And so m sub x is equal to 5 times 2 for the first mass, plus 4 times 5 for the second, plus 3 times 2 for the third, plus 6 times -2 for the fourth. That sum is 24. These are the moments about, sorry, I was just thinking, these are the moments that make our lives. These are the moments about the y-axis and the x-axis. In and of themselves, they tell us a little bit of information, but they can be used to find the center of mass of a system. X bar is equal to m sub y over m, where and that x bar, it's read that way out loud. Looks like x with a little hat on it. And m is the total mass. and keep going. Y bar is equal to m sub x divided by m, the total mass. And the center of mass has coordinates x bar, y bar. To see why these expressions for x bar and y bar should make sense, we're going to consider point masses balanced at a point x bar. And when I say that, we're considering on the x-axis a balancing point x bar, to the left of which we have x1, at which is point mass m1, and then we have to the right of x bar x2, at which is mass m2. This will balance at x bar if the distance times the mass in each direction is equal to each other. The distance between x bar and x1 is just the difference, x bar minus x1. And so m1 times that distance should equal m2 times the distance x2 minus x bar. Distributing, we get m1 x bar minus m1 x1 is equal to m2 x2 minus m2 x bar. And solving for x bar, we get that x bar is equal to m1 x1 plus m2 x2 over m1 plus m2. And in the numerator, we have the sum of mass times distances. And in the denominator, we have the sum of the masses. So this agrees with what we had above, my over m for x bar and mx over m for y bar. With that, these formulas should make sense. And so if we take a moment about the y-axis and divide it by the total mass, then we get the x-coordinate of the center of mass, which is x bar, likewise y bar. In our case here, our total mass is just the sum of the masses that we had. And so 5 plus 4 plus 3 plus 6 is the total mass. That gives us a sum of 18. For the center of mass then, we're looking at negative 5 over 18, the moment about the y-axis divided by the total mass, and then 24 divided by 18 for the y-coordinate, which of course reduces to 4/3. So the center of mass is negative 5/18, 4/3. The moment about the y-axis is negative 5. The moment about the x-axis is 24. Visually here, negative 5/18 is about 1/3, and then 4/3 is a little bit more than 1. And so what we find is that the center of mass of the system is in the second quadrant at coordinates negative 5/18, 4/3. That's the point where this system would balance. Put a different way, if all of the mass in this system were located at that center of mass, then the moments about the y-axis and the x-axis would remain unchanged.